Welcome to another Algebra 2 lesson. This is lesson 5.2, our objective. Use properties of rational exponents and radicals to simplify expressions. Simplify. X to the negative 1 power. When we are simplifying, we are not allowed to have a negative exponent in our final answer. Negative exponents give us reciprocals. So x to the negative 1 equals 1 over x. Number 2, remember that an exponent only applies to whatever is directly to the left of it. The only time an exponent applies to more than one thing is when it is next to parentheses. So the 3 stays in the numerator. The x to the negative 6th power will become x to the positive 6th power when we put it in the denominator. Number 3, we have a negative exponent in the denominator, so we're going to move it up to the numerator to make it positive. Number 4, a b to the 4th to the 1st power. Well, that's just a b to the 4th. For it to be simplified, we have to remove any parentheses and make sure we do not have any negative exponents. Number 5, y to the 6th over y to the 4th. That is the same as y to the 6th times y to the negative 4th. So add our exponents. 6 minus 4 is 2. Another way to think of that problem is you could write out 6y's on the top, 4y's on the bottom, because y to the 6th means y times y times y times y times y times y. And on the bottom we have y to the 4th. So y divided by y is 1. 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 And there are 2 y's left being multiplied together, y squared. Okay, what about this one? P to the 4th on the top and just p on the bottom. So 1p gets canceled out. How many are left? 3 of them. P times p times p is p cubed. All right, these are just kind of some warm-up problems. You should have seen some exponent rules before, but we've got to take our exponent rules and apply them also to rational exponents, like we saw in 5.1, exponents with fractions. Here's a reminder of all the rules we should know about exponents. Product of powers. When you multiply 2 powers with the same base, the shortcut is to add the exponents. We have to be able to apply this to fraction exponents. 5 to the 1/2 times 5 to the 3/2 will be 5 to the 1/2 plus 3/2. 1/2 plus 3/2 is 4/2. 4/2 is 2. So 5 squared is 25. Raising a power to a power, we multiply our exponents. Power of a product, if we have 2 things in parentheses raised to a power, each one of them will get that power. Negative exponents give us reciprocals. Anything to the 0 power is 1. Quotient of powers, subtract your exponents. Power of a quotient, if we have parentheses, both things will get that power. So that, notice it also applies to our fraction exponents. Here we go. 7 to the 1/4 times 7 to the 1/2 power. Multiplying 2 powers with the same base, the big number, the 7, is called your base number. Multiplying 2 powers with the same base, we add the exponents. So 1/4 plus 1/2. When you're adding fractions, you have to get a common denominator. 1/4 plus 1/2, you have to get a common denominator of a 4. by multiplying by some form of the number 1. So we get 1/4 plus 2/4 is 3/4. So we get 7 to the 3/4 power. Next one, 6 to the 1/2 power times 4 to the 1/3 power, all of that squared. The exponent of the 2 is next to parentheses, so it affects everything inside those parentheses. And when you raise a power to a power, you need to multiply. So we get 6 to the 1/2 squared, and we have 4 to the 1/3 squared. Power to a power, multiply your exponents. What's half of 2? Yep, half of 2 is 1. And then we're also going to do the 4 to the 1/3 squared. So that's 1/3 times 2. Half of 2 is 1. 1/3 times 2 is 2/3. So 6 to the 1 is just 6, and 4 to the 2/3 power, we have to leave that as 4 2/3. There's our final answer. And the next one, 4 to the 5th times 3 to the 5th. Ooh, notice they both have a exponent of a 5. That means we can group those together as 4 times 3 to the 5th power, because you can only do that when that exponent's the same. So 4 times 3 is going to give us a 12. 12 to the 5th power to the negative 1/5 power. Now multiply your exponents, raising a power to a power. You're going to multiply those exponents. Negative 1/5 times 5 is negative 1. And what's 12 to the negative 1? Remember, negative exponents give us reciprocals. 1/12. And that's our first set of examples with fraction exponents. Oh, 2 more. 5 divided by 5 to the 1/3. Subtract your exponents because it's division. 1 minus 1/3 is 2/3. Here we have 42 to the 1/3 over 6 to the 1/3. Those exponents match. That means we can put that 42 and 6 together. 42 divided by 6 is 7. So we're going to get a 7 to the 1/3 and then squared. Raising a power to a power, multiply your exponents. 1/3 times 2 is 2/3. And there's your final answer there. Remember, these examples are also in your book, your e-book. Let's try some more. The more we practice, the better we get. 2 to the 3/4 times 2 to the 1/2. Multiplying two powers with the same base, we need to add our exponents. 3/4 plus 1/2. We need 1/2 to be in fourths. So multiply numerator and denominator both by 2. So we get 3/4 plus 2/4. That's 5/4. So our answer is 2 to the 5/4 power. Number 2. When you don't have an exponent, you can fill in a 1. This is 3 to the 1 minus 1/4 power. We could get a common denominator, but I just think about pizzas. If I have one whole pizza and someone eats a fourth of it, 1/4, how much do I have left? 3, take away 1/4, there is 3/4 left. 3 and 3. 3 to the 3/4 power. Next one. Notice these both have the same exponent. So we can remove it from them and put parentheses. That helps us because we can do 20 divided by 5 is 4. And then we have 4 to the 1/2 and a 3 out here. So that's 4 to the 3/2 power. Next one, 5 to the 1/3 times 7 to the 1/4, both cubed. So 1/3 times 3, and 7 to the 1/4 times 3 power. So 1/3 times 3, 1/3 of 3 is 1, so that's just 5. 1/4 times 3 is 3/4. And there we go. Now, I'm not sure if Big Ideas will take this answer, 4 to the 3/2, if they just wanted you to do the exponent rules, or if they wanted you to simplify some more. Think about a 1/2 power. 1/2 power is also a square root. What is the square root of 4? Square root of 4 is 2. So they might want 4 to the 3/2. They might take 2 cubed, but 2 cubed we also know is 2 times 2 times 2. So that's 8. I'm not sure which version of the answer they're going to want. To simplify it and completely simplify it, final answer for this one should be 8. 2 to the 5/4, that's as far as it goes, and same with these other answers. Not any choices there. All right, that was our guided practice. What about radicals? Well, if it applies to fraction exponents, radicals can be written as fraction exponents. Keep that in mind. If we have an nth root of a times b, we can separate it nth root of a times nth root of b. If we have the nth root of a divided by b, we can separate that into the nth root of a over the nth root of b. So we can separate it or we can put it back together, whichever helps us simplify easier. It applied to square roots, now it also applies to nth roots. Example 2. Cube root of 12 times cube root of 18. Product property of radicals says if they're both cube roots and we're multiplying, we can put them together in one radical. What is 12 times 18? $216. And what's the cube root of 216? 6. Okay, another way to have simplified that without grabbing a calculator, 12 is 2 times 3. Times another 2. 2 times 2 times 3. 2 times 2 is 4, times 3 is 12. So prime factors of 12 are 2 times 2 times 3. 18. 18 is 9 times 2, or 2 times 3 times 3. We've talked about popping out pairs with square roots, but when we're doing a cube root, we're looking for sets of 3. We have 3 2's, so a 2 pops out. We have 1, 2, 3 3's, so a 3 pops out. Then multiply those together. 2 times 3 is 6. We don't need a calculator. There it is. We had a set of 3's and a set of 2's. 2 times 3 is 6. All right, next problem. 4th root of 80 over 4th root of 5. They're both a 4th root. We can put it together. You can do your division. 80 divided by 5 is 16. 4th root of 16. Think about a factor tree. 16 is 4 times 4. 4 is 2 times 2. Another 2 times 2. So it's 2 times 2 times 2 times 2, which is 2 to the 4th. 4th root of 2 to the 4th is 2. So there's our answer. An expression involving a radical with index n is in simplest form when these 3 conditions are met. No radicands have perfect nth powers as factors other than 1. So in other words, like if we're doing a cube root and we have a set of 3 of them, we've got to pop it out. The radicand is the thing inside the radical. No radicands contain fractions. No radicals appear in the denominator of a fraction. To meet the last 2 conditions, rationalize the denominator. This involves multiplying both the numerator and denominator by an appropriate form of 1 that creates a perfect nth power in the denominator. Okay, we've got some work to do with rationalizing the denominator. Write each expression in simplest form. Cube root of 135. Make a factor tree. I know it's divisible by 5 because it ends in a 5. (135) divided by 5 is 27. Break down your 27. So we have the cube root of 3 times 3 times 3 times 5. To simplify a cube root, we're looking for sets of 3 identical factors. We have 3 3's, so those 3 3's pop out of the radical, become 1 3. That's 27. 3 times 3 times 3 is 27. Cube root of 27 is 3. You can check it on a calculator if you don't believe me, but we're looking for sets of 3 when we're doing a cube root. We want to tuck that index kind of in between that little area there so that we know it's not an exponent of the 3 and that it goes with the radical. Okay, so 3 cube root of 5. The 5 stays inside because there weren't 3 of them, and we would need 3 of them for it to pop out. All right, next one. Going to have to rationalize the denominator. We could do the 5th root of 7 over 8, but if you look at the rules, we're not allowed to have a fraction in the exponent. Sorry, a fraction in the radical sign, inside the radical, and we are not allowed to leave a radical in the denominator. So this is a 5th root. 8 is 2 times 2 times 2. It's going to help us figure out what we need to do if I write it this way. We need a set of 5 2's for it to pop out. 7 is already prime, so I can't simplify that at all. Can't break it down. What we have to do is multiply by a form of the number 1 so that we're changing the appearance but not to the value of our fraction of this number, is we're going to multiply it by the 5th root of something so that we have 5 2's. We already have 3. How many more do we need? We need a set of 5. So we need 2 more 2's. Whatever I multiply the bottom by, I also have to do on the top. All right, this gives us 5 2's on the bottom, so we get just a 2 for our denominator. Is the 5th root of 2 times 2 times 2 times 2 times 2 is 2. And then in our numerator, we have the 5th root, tuck in that 5, of 7 times 2 times 2. What is 7 times 2 times 2? Well, I'm going to go in this order. 2 times 2 is 4. 4 times 7 is 28. And that's our final answer. 5th root of 28 over 2. Notice the radical is now just in the numerator. That is considered simplest form. We did not change the value of the number. We only multiplied by the number 1. Anything divided by itself is just 1. We changed the appearance without changing the value. All right, there's 2 examples of simplifying. This one, we had the rationalized denominator. Well, what if our denominator has something like 5 plus rad 3? We still have to get that radical out of the denominator. For denominators, that is a sum or difference involving square roots. Multiply both the numerator and denominator by the conjugate of the denominator. The expressions a rad b plus c rad d and a rad b minus c rad d are conjugates of each other, where a, b, c, and d are rational numbers. So what is the conjugate value of 5 plus rad 3? Notice the difference. Just change, one has to be plus and one has to be minus. So this has a 5 plus rad 3. So we are going to multiply by 5 minus rad 3. But we're just simplifying. Whatever we do to the numerator or to the denominator, we also have to do to the numerator. So when we multiply the bottom by 5 minus rad 3, we also have to do that on the top. Then we are only multiplying by a form of the number 1. So this is what we need to do to rationalize the denominator. Multiplying top and bottom by the conjugate. Numerator and denominator by the conjugate of the denominator. All right, here we go. On the top, 5 minus rad 3. That was easy. Just had to multiply by 1. Now in the denominator, we have 4 multiplications to do. Here we go. Multiply. Multiply. Now multiply by rad 3. One more multiplication. Positive rad 3 times negative rad 3. That's negative rad 9. Oh, but the square root of 9 is 3. So we have 25 minus 5 rad 3 plus 5 rad 3. That makes a 0. And then we have 25 minus 3. 22. 5 minus rad 3 over 22. We rationalize the denominator by multiplying the numerator and denominator by the conjugate of the denominator. Now it's in simplest form. All right, adding and subtracting expressions with radicals. Okay, think objects. 1 pineapple plus 7 pineapples is 8 pineapples. 2 elephants plus 10 elephants is 12 elephants. Good. So far, so good, right? 1 pineapple plus 7 pineapples is 8 pineapples. 2 elephants plus 10 elephants is 12 elephants. They must be like terms to add or subtract. Radical expressions must have the same index and radicand, so thing inside the radical, and the same number on the radical, like down here, cube root, cube root. Oh, but those don't match in there. We're going to have to talk about that. Okay, so if they are like terms, then we can add them together. 4 rad 10 plus, fourth root of 10 plus 7 times the fourth root of 10. So we have 1 fourth root of 10 plus 7 fourth root of 10s. That's 1 pineapple plus 7 pineapples is 8 pineapples. But they're not pineapples. It's this thing. 1 of these plus 7 more of these is 8 of these. So it's 8 fourth root of 10s. That's our answer. It was just like the pineapples. All right, so where's the elephants? 2 elephants plus 10 elephants. Oh, here they are. 2 elephants plus 10 elephants. 2 elephants plus 10 elephants is 12 elephants. But this time our elephants are not elephants. They are 8 to the 1/5 power. But that's what we have 12 of. So 12, 8 to the 1/5 power. Next one, cube root of 54, cube root of 2. Well, 54 that's not prime numbers. We need to break that down. So 54 is even. Divide by 2, we get 27. 27 is 3 times 9. 9 is 3 times 3. So let's simplify cube root of 54. This is 3 3s and a 2. And we're doing a cube root. So we're looking for sets of 3 to pop out. Oh, we had 3 3s. So we pop out a 3. And we only have 1 2. So the 2 stays in. 3 pops out, 2 stays in. What kind of root? A cube root. Make sure to write your index there. If you accidentally leave it off, it counts as a square root. So we have 3 cube root of 2's minus 1 cube root of 2's. Very helpful to put that 1 in there. Invisible 1 coefficient like I did over here. 1 plus 7 was 8. 3 minus 1 is 2. 3 of these minus 1 of these is 2 of these. So it's 2 cube root of 2. All right, these were like terms. They had the same index and same radicand. So it's cube root of 2, cube root of 2. 3 minus 1 of them is 2. 2 cube root of 2. When n is odd, the nth root of x to the n is just x. When n is even, the nth root of x to the n is the absolute value of x. In most situations, they'll just tell us that they're positive numbers and we don't have to worry about this. But every now and then they don't do that. So because a variable can be positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression. So this one, cube root of 64, y to the 6th. Well, 64 is 8 times 8. 8 is 2 times 2 times 2. 2 times 2 is 4, times 1 2 is 8. And this 8 is 2 times 2 times 2. So that's 6 2's. We have 2 sets of 3. So we pop out a 2. We pop out another 2. 64 is gone. And then y to the 6th. We have 6 y's. That's one set of 3 and another set of 3. So we get 2 times 2 is 4. Y times y is y squared. Okay, so here we go. If we take the time to write it out, we get a set of 3. That became, these 3 2's became 1 2. These 3 2's became 1 2 outside because we're looking for sets of 3. Then we had one set of 3 y's and a second set of 3 y's. And that's why it was 4y squared. Now, there's got to be a shortcut to this, right? So it's 2 to the 6th and y to the 6th. Well, remember, when we rewrote these as fraction exponents, that was the same as y to the 6th divided by 3. The index became the denominator of the exponent. 6/3, that's 2. So let's think about that with this one. X to the 4th to the 4th root, that's x to the 4/4 power, and y 8/4 power. What's 4 divided by 4? 1. And what is 8 divided by 4? 2. Okay, let's look at the book solution. They separated it, and then they even looked at this as y squared to the 4th, and got y squared. Now, they put absolute values here. Think about what we had back at the top of the page. When n is even, the nth root of x to the n is the absolute value. So they didn't put absolute values here on the y because they're squaring it, which would turn it positive anyway. So to fix our answer, we would want to put, I don't need that one there, absolute value of x over y squared. And this is your final answer. All right, so when we do an even root, we have to worry about absolute values sometimes. When we have an odd root, it doesn't matter because y could be positive or negative. Example 7, write each expression in simplest form. Assume all variables are positive. See, when they tell us this, then we don't have to worry about absolute values. So don't worry about absolute values. We are looking for sets of 5. This first one, example 7a, sets of 5. So 4 is 2 times 2. So that's not going anywhere. We don't have a set of 5 of anything. So I'm going to write my radical so I can have space to write things in front of it and behind it. So I have my 5th root. The 4 is going to stay in the radical. We have a to the 8th. If you write them all out, that's a times 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 a. We have one set of 5, so we get an a on the outside. We get one a on the outside. That takes away 5 of these. How many are left? 3. There's 3 left, so that's a cubed still on the inside. And what about b? So basically we're dividing. 14 divided by 5 is 2. There are 2 sets of 5 in 14. So we get a b squared out here for those 2 sets of 5 b's. And then how many are left? That takes away 10 of them. There's 4 left. So there's 4 left over. And then c to the 5th, 5th root of c to the 5th power, that's one group of 5. So that's c to the 1st power, no c's left inside. All right, let's write this for our final answer. We don't need these ones, so we have a b squared c times the 5th root. I want to tuck my 5 in so I know it's part of my index. The 5th root of 4 a cubed b to the 4th. And that's our final answer. All right, let's try the next one. Okay, we have x, and we have a y to the 8th to the 3rd power. We need it to be even sets of 3. So what I'm going to do is I'm just going to do this right here. We need sets of 3. So we need a multiple of 3 for this exponent. If we make that 8 a 9, that's a multiple of 3. So I'm going to multiply the top and the bottom by the cube root of y. So our problem now becomes x cube root of y over y cube root of y to the 9th. Well, the cube root of y to the 9th is just y cubed. So our new denominator is y cubed, but our numerator is x times. Make sure you tuck in that index so we know that that's not an. See here, it kind of looked like an exponent of the x and kind of looked like part of the radical. It was hard to tell which. So I like to tuck it in that little piece of the radical sign right there. All right, x times cube root of y all over y cubed. Next one, here we go. 14 divided by 2 is 7. Then we have an x. No exponent here. Okay, we've got fraction exponents. Oh, goodness. A little harder to add and subtract, so we're going to write it out for now. 1 minus 3/4. And then a y. No y's on the bottom, so just that exponent stays the same. Y to the 1/3 power. Then look at our z's. Look at our z's. There's no z on the top, but we have a z on the bottom. But it's a negative exponent. So rewrite it as a positive exponent. It has to change locations. Negative exponents give us reciprocals. So when we move it up to the numerator, it becomes a positive 6. All right, 1 minus 3/4. 1 minus 3/4 is 1/4. The y, just need to rewrite that. It has a 1/3 exponent. And our z has a 6 for an exponent. There's our answer to 7C. Simplest form, assume all variables are positive, so we didn't have to worry about absolute values. Example 8, perform each indicated operation, assume all variables are positive. All right, this is like our pineapples and elephants. We have 5, let's go with this, flowers. 5 flowers plus 6 flowers. 5 objects plus 6 more of the same object. 5 plus 6 is 11. 11 what? 11 square root of y. Over here, 12 cube root of 2z to the 5th minus z cube root of 54z squared. Oh man, 54. Break it down. We did this one earlier. 54 is 2 times 27. 2 times 27. So we get 3 3s, and we're doing a cube root, so the 3 pops out. The 2 stays in. There was already a z on the outside, so the 3 joins the z on the outside. Then we have a cube root of, leave the 2 inside, z squared. Okay, I put a little slash through my z's because otherwise they look a bit like my 2's. So we have 12. Now are they like terms? They weren't before. At least they didn't look like it. Oh, we can't leave a z to the 5th. We have to simplify this one also. Okay, simplify both of them individually. Then we can subtract if they're like terms. All right, z to the 5th, we can pop out a z. So we have a 12. Pop out a z. That takes care of 3 of those z's with 2 left inside. Now are they like terms? Yes, they are. Look, this part here. Cube root of 2z squared, cube root of 2z squared. So we have 12z minus 3z of these things. So there's our cube root of 2z squared. 12z minus 3z is 9z. And that's our final answer. 9z times cube root of 2z squared. Simplify both of them first. Make sure they're like terms. Then if they're like terms, then we can subtract. Put that a little closer together. That looks better. And that's it for our 5.2 notes and all of our examples. You had lots of examples in that one. These problems don't take as long for each individual problem, so we get lots and lots of problems to work on. The more you practice, the better you get. All right, please work on your big ideas assignment 5.2. Have a great day.